If you are storing sodium hypochlorite at trade-grade concentrations, your current chemical storage tank is likely an incorrect specification waiting to fail. The industry pattern is consistent. A water treatment plant experiences a sudden, catastrophic loss of containment. Thousands of gallons of corrosive oxidizer flood the floor. The facility managers scramble to clean up the spill and mitigate the damage, often concluding the process by ordering an identical, high-density polyethylene replacement tank directly from a catalog. Look at the financial exposure on this chart. An emergency tank replacement costs up to $40,000. Facility downtime adds $80,000. Throw in a minimum $25,000 EPA penalty, and a single failure creates a $250,000 liability. These ruptures represent a predictable material science failure triggered by specifying the wrong resin for an oxidizing chemical. We will autopsy exactly why standard linear polyethylene fails in sodium hypochlorite service and reconstruct the engineering specification required to build a zero-failure system. Saving $3,000 upfront on the wrong tank resin creates a massive future risk profile. Material selection is the entire financial decision. Sodium hypochlorite at trade concentrations between 10 and 15% is a severe oxidizing agent. Standard HDPE consists of linear polymer chains. Notice how these chains lie parallel to one another, held together only by weak intermolecular forces. There are no covalent bonds holding adjacent chains together. Oxidizing ions from the hypochlorite penetrate the gaps in this matrix, attacking the carbon-hydrogen backbone and breaking the long chains into brittle, disconnected segments. This initiates environmental stress cracking. Because the structure is linear, a single microfracture rapidly unzips along the parallel lines, tearing the tank wall entirely in half. The engineering solution requires a completely different molecular architecture, cross-linked polyethylene, or XLPE. The rotational molding process creates permanent covalent bonds between the polymer chains. This three-dimensional cross-linked network resists oxidative attack and stops crack propagation in its tracks. But for sodium hypochlorite concentrations over 1%, a cross-linked matrix alone is not enough. The specification requires a secondary barrier, the OR1000 antioxidant system. OR1000 is a sacrificial antioxidant package molded directly into the interior wetted surface. It actively absorbs and neutralizes incoming oxidizers before they ever reach the structural XLPE matrix behind it. Omitting cross-linking and an integrated antioxidant barrier guarantees molecular degradation. XLPE with OR1000 is mandatory for long-term survival in hypochlorite service. Oxidative attack compromises the material, but the actual rupture almost always initiates at the point of highest physical stress, the lower sidewall. Standard tanks use through-wall bulkhead fittings. Punching a hole through the base of the sidewall creates a mechanical compression joint exactly where the internal hydrostatic pressure is at its maximum. Polyethylene expands and contracts with temperature. That thermal cycling, combined with vibration from rigid discharge piping, creates constant bending stress that eventually fractures this mechanical joint. This sidewall geometry creates a secondary chemical problem. A residual heel of chemical remains permanently trapped on the flat floor below the fitting. That trapped hypochlorite continuously decomposes in place, off-gassing chlorine and diluting the active concentration of every fresh chemical delivery you pump into the tank. The specification to solve both the mechanical and chemical flaws is the integrally molded flanged outlet, known as the IMFO system. The IMFO eliminates the through-wall penetration. The outlet flange is molded continuously into the sloped floor as a single piece of polyethylene, removing the vulnerable mechanical joint entirely. This sloped geometry directs liquid to the absolute lowest point, ensuring complete zero-heel gravity drainage. To protect the newly unified structure, the system requires a bellows transition fitting between the IMFO and the rigid discharge piping to decouple any external vibration from the tank body. Removing the mechanical joint and the chemical heel simultaneously solves the physical stress failure and neutralizes the continuous degradation vulnerability. Even with a structurally optimized primary vessel, operating a single-wall chemical tank indoors creates a severe vulnerability, uncontained release. The traditional response is to pour a concrete secondary containment basin. But concrete requires massive facility footprints, demands expensive construction lead times, and degrades rapidly under repeated chlorine exposure. This diagram details the Processing Safe Tank double wall system. It integrates an inner XLPE primary vessel directly inside a cross-linked outer containment wall. EPA SPCC regulations require secondary containment to hold 110% of the primary vessel's capacity. If the inner tank fails, the chemical floods the interstitial space, remaining perfectly contained well below the outer rim. That interstitial space between the walls also allows for safe, integrated leak detection monitoring without exposing personnel to the chemical. This double wall configuration delivers full regulatory compliance within the exact same square footage as a standard single wall tank. True risk mitigation means internalizing secondary containment to eliminate external environmental liabilities and bypass tens of thousands of dollars in concrete infrastructure costs. An engineered XLPE primary tank will still fail if the external accessories are improperly specified. For outdoor installations, the tank shell must be opaque. Direct sunlight degrades linear polyethylene and rapidly accelerates sodium hypochlorite decomposition. The piping specification is absolute. All wetted fittings must be PVC or CPVC. Zero metallic parts are permitted in the fluid path. Trace amounts of iron, copper, brass, or zinc act as immediate catalysts. They trigger rapid hypochlorite decomposition, producing localized corrosion and violent chlorine off-gassing. Level indication requires magnetic float gauges. Hypochlorite at trade grade is opaque, making standard polysite columns useless, and the chemistry aggressively attacks glass. Because the chemical continuously generates gas, tanks must route their vents safely outdoors, or through an activated carbon scrubber system to prevent hazardous chlorine accumulation in operator workspaces. This checklist outlines the required parameters. A zero-failure system demands that every component, from the primary vessel down to the smallest fitting, is strictly governed by the chemical's aggressive oxidative properties. Engineering precision ultimately translates directly to procurement reality, total cost of ownership. This chart compares the actual financial impact over 5 years. The top timeline tracks a standard HDPE specification, hitting catastrophic cost spikes exceeding $100,000 across multiple replacement cycles. The bottom timeline shows a correctly specified XLPE system, holding a flat, predictable baseline near $20,000. Cross-linked polyethylene and double-wall containment satisfy the specific chemical compatibility requirements of trade-grade bleach. A tank rupture occurs as the mathematical result of an insufficient specification. Liberty Chemical Equipment and Supply engineers complete zero-failure compliance systems tailored to each facility. Over the past 30 years, Liberty CES expert James Riggins has specified more than 100 chemical feed projects with exactly 0 specification-related failures. Before you issue a purchase order for a chemical storage system, contact the Liberty CES engineering line to verify your exact chemical, concentration, and temperature parameters. Because the correct specification costs vastly less than a single failure incident, the XLPE specification is the only defensible engineering choice for sodium hypochlorite storage.